Uh, the speaker is Himanshu Raj, and he will be speaking about M theory aptitudes from 6D. Please.
Okay, so thanks Aditya for asking me to give this presentation. So I will be speaking on work that I've been doing in collaboration with Fernando Elde and Shai Chester, who is a postdoc here at Weizmann. And this work is largely based on computing or reconstructing scattering amplitudes in M theory on certain compactifications, certain ADS compactifications using analytic conformal bootstrap in the dual superconformal field, in the respective dual superconformal field theories. So this would be 62,0 and the 3D n equals to 8 ABJM. So the main idea behind this project is the following. So we know that ADS-CFT correspondence maps correlation functions of local operators in a conformal field theory to scattering amplitudes of dual fields in string or M theory on ADS space. Um, Computing such amplitudes from first principles in ADS space is quite hard, and there have been only very limited progress beyond the semi-classical limit, beyond the tree level. However, the large and analytic bootstrap technique, which was initiated by in this paper by Hermsik, Pendones, Polchinski, and Sully, and was further extended by Ofer Aroni here at Weizmann, Fernando Elde, BC, and Permuter, which allows us to overcome this difficulty to a certain extent. These methods are applicable to generic large N or large central charge conformal field theories, and, and they allow us to compute correlation functions in a 1 over C expansion, which then maps to corresponding loop expansion of scattering amplitudes in ADS. Furthermore, in maximally supersymmetric cases, like the n equals to 4 super Yang-Mills or the 62,0 superconformal field theories, or the 3D n equals to 8 ABGM theories, there are much further constraints, specifically because of maximal supersymmetry, that allows us to fix the correlators at tree level completely up to a finite number of ambiguities. This was initiated in the seminal work by Rastelli and Zhao in 2017, and there have been significant progress in this direction of computing tree-level ADS amplitudes in maximally superconformal field theories for arbitrary operators. By the way, if there are any questions, please feel free to ask. Otherwise, it will be not very interesting to present. Um, okay. Um, so what we will do in this talk is to apply the methods which were developed in these papers to reproduce the one loop amplitude of 4 graviton scattering in 11-dimensional supergravity, which is the low energy effective theory of M theory, low energy effective description of M theory, on ADS 7 times S4 and on ADS 4 times S7, which are solutions to 11-dimensional supergravity, by calculating stress tensor 4-point functions in the respective dual superconformal field theories, which are the 6-dimensional 2,0 theories and the 3D n equals to 8 ABGM theories. And we'll do this in a 1 over C expansion. Yeah.
So why specifically two spaces? I mean, why? I mean, what's special about the two spaces that you have here?
One reason is that these are the simplest solutions of 11-dimensional supergravity, for which we know the precise ADS-CFT pair. I mean, the conjecture has been well established. And this is the next harder case, if you want, as compared to n equals to 4 super Yang-Mills. So this problem that I'm going to present here was already
I see.
solved for n equals to 4 super Yang-Mills, which is
Right.
due to type 2b superstring theory on ADS 5 times S5.
Yeah.
And this was like to sort of see if such a computation can be done, or at least demonstrated, for the next simplest case, which are these two.
Okay, thanks.
Yeah. So let's begin. Let me review by first saying a few like the form of the M theory scattering amplitude. So the M theory effective action, which is the 11-dimensional supergravity, takes the following form. So we have the usual the Ricci's Einstein-Hilbert term, which is the Ricci scalar here. Then we have a tower of higher derivative corrections that starts from r to the 4, d to the, then it goes to d to the 6 r to the 4, and then d to the 8 r to the 4, and so on. The d to the 4 r to the 4 term in M theory was computed to be vanishing. So the coefficient of that term vanishes in M theory. And other lower derivative terms do not appear here on account of supersymmetry. So this is the form of the 11-dimensional supergravity action. What is unknown here are these coefficients alpha, beta, and gamma, and so on, the coefficients of the of these higher derivative terms. So all that is known about M theory till date are the coefficients alpha and beta. Okay, and then the reason that we know this is because r to the 4 and d to the 6 r to the 4, these two terms are protected by supersymmetry. So that's the reason that people have been able to compute alpha and beta, basically through compactifying the theory on a torus, on an S1, and then matching it with the corresponding results in string theory. The d to the 8 r to the 4 and higher derivative terms are not protected by supersymmetry, and therefore their coefficients are unknown. So this is the form of the action. And this kappa 11 is related to the 11-dimensional Planck constant in the following way. Okay, so that's for the action. Then the 11-dimensional scattering amplitude itself takes the following form, which is and this form is fixed basically by supersymmetry word identities. Okay, so first of all, the first thing to note that there is this function k hat, which encodes all the polarizations, and the moment is a function of the polarization. So it encodes basically all the polarizations, and is also a function of the momenta of the external four gravitons. So that's that. And then we have a contribution, and then goes so first of all, I've pulled like 1 over STU outside, and because of that, there's a normalization here, which is 1, and this one is the contribution from the supergravity vertex R here, the Einstein-Hilbert term. So this one corresponds to the R in the action. So this is the first term. Then we have a tower of analytic terms which are analytic in S and T. Um, and these are in one-to-one correspondence with the higher derivative terms that we see in the action. Beyond this, we have the non-analytic pieces, which are composed of the analytic pieces which are composed of the lower order analytic pieces through unitarity cuts. So so um, so um, so as I was saying before, because we know the alpha and beta in the action, we know correspondingly what are these f's corresponding to the r to the 4 term and the d to the 6 r to the 4 term in the 11-dimensional scattering amplitudes, and which they take this particular form. And this is all that is known so far. Um, so one of the early breakthroughs in reproducing this form of the action from the dual superconformal field theory was done in this paper by Chichester and Eric Permuter, and in a previous paper by Sheehan, Sylvie Pufu, and Chichester. where they were able to reproduce this r to the 4 term and the d to the 6 r to the 4 term purely from the respective the superconformal field theory, which are dual to M theory on areas 7 times S4 and areas 4 times S7. Um, they were able to reproduce just the R to the 4 term. The D to the 6 R to the 4 term was not possible to reproduce. But it was still they were still possible to extract this piece just purely from CFT calculations. What we will do today is to reproduce now the non-analytic pieces, which corresponds to loops in 11 dimension. So this is uh, the target. Okay.
Okay.
Okay. So yeah. So let me just summarize in slightly different words. What we will do is to compute the connected 4-point function of energy momentum tensor in the dual superconformal field theories in a 1 over central charge expansion. Okay. Then the area CFT maps the above quantity to the 4-point graviton scattering in 11 dimensions on areas times the sphere. And these will take the following form. Okay. Now, this is the amplitude in areas times S. When we take the flat space limit, that means we take the respective radius to be infinite. It should be the case that the one loop amplitudes in areas should precisely match onto the respective one loop amplitudes in 11 dimensions. So this is one of the things that we expect, and in this talk we will show this. Okay, so let's now delve into some background. So from now on, I will mostly focus on the 6D2,0 theory as a specific case. The 3D n equals to 8 ABJM theory can also be treated analogously. The details are of course very different, but the basic idea is the same. I will comment on 3D n equals to 8 at the end of the talk, but the bulk of the talk will now be just focusing on the 62,0. So M theory on area 7 times S4 with n units of 4-form flux on the 4 sphere is conjectured to be dual to an elusive 6-dimensional 2,0 theory of the AN type, whose central charge is given by this quantity, and at large n it scales like 4n cube. The length of the areas and the Planck constant are related to the central charge in this particular manner. And the length of the areas space, the radius of the areas 7 and the radius of S4 are related to each other in this particular manner. One is half of the other. So this is one particular class of 2,0 theories. There's another class of 62,0 theories, which are which are the so-called DN theories. And these are holographically dual to M theory on area 7 times the Z2 orbifold of S4. And in this theory, the central charge also scales like n cube, but the overall coefficient is slightly different. These theories are strongly coupled, and these two are the only theories, only 6-dimensional 2,0 theories that admit a large n description, and they are strongly coupled for any value of n. There is actually no coupling constant in this theory.
Excuse me, what sort of an RP fold is this? Is this like an RP4? The S4 mod set to
Yeah,
what
yeah,
kind of yeah, so
yeah,
is this like is this an RP4?
yeah, yeah.
Okay, okay,
It's an RP4.
okay.
Um, yeah, and we'll see what the action of Z2 is. So I mean, this has so this was on the area side, and on the CFT side, the effect of the Z2 will be to project out certain operators. Basically, that's the
Okay,
operation
okay.
that it does.
And I don't know about this. What is the I mean, you have an AN and TN, so I imagine you also have an E6, E7, E8.
Yeah. So the actually I don't know if the full classification of all possible 2,0 theories in 6 dimension is known, but at least the ADE kind of theories are known, and they were conjectured to be arising as the decoupling limit of um, the world volume, and the decoupling limit of M theory that arises when we put M5 branes on ALE spaces, and they
Yeah.
are labeled by this simply laced Lie algebras of which are of the ADE type.
Right.
But apart from this, I don't know anything. I mean, so this is the only thing that, okay, I mean, like we know the spectrum of these. Okay, I was about to say that, but we know these AN and the DN theories. And on top of that, as you correctly said, that there are also these series of EN theories. But the thing is that those theories do not have a large N limit. Their rank is fixed.
Yes,
On the other hand, for AN and DN, we can tune N, and for large N, we can apply the techniques that I'm going to discuss, this large N conformal bootstrap technique.
I see. And what sort of a space would it be for E6, E7, and E8? I mean, like you have.
So that would be, so as I said, I mean, this ADS 7 times S4 and ADS 7 times S4 mod Z2 is a if you want like a region, or sorry, is a solution to the 11-dimensional supergravity, right? So it's in the supergravity approximation where N is large,
Oh,
right?
right, right, right. Okay, okay, okay.
But
Yeah,
for
yeah.
the EN theories, presumably there is such a space, but it's not, it will not be captured by the supergravity approximation.
Okay. Yeah.
I mean, it has to be embedded in the, like it has to be described by the full M theory and the M2 brain, M5 brains. Yeah, I mean, for example, yeah, I mean, I don't know if I can give another example. I mean, okay, there's no worldsheet here. I mean, if there was a worldsheet description, I could have said that there is a description in terms of in terms of a two-dimensional sigma model, right? Um,
Yeah.
but here there is okay. Anyway, so yeah. Okay, so these are the two theories that we'll be interested in this talk.
Okay.
Um, okay, so the spectrum of single trace local operators is also known in these theories, and these are dual to the Kaluza-Klein modes of 11T graviton multiplet on ADS 7 times S4. The operators in the DN theory are obtained from the corresponding spectrum of operators in the AN minus 1 theory by a Z2 projection. And I will show how this Z2 projection act when I tell what the operators are. So to study the operators, first we have to review a bit of the irreducible representations of the corresponding superconformal algebra. So the algebra in this case is OSP 8 star slash 4. And the bosonic part of this algebra is the SO6, comma 2, which is a conformal group in 6 dimensions, and the SO5 group, SO5 algebra, which is the R symmetry algebra. All local operators in the theory can be classified by representations under under the bosonic subalgebra of OSP 8 star slash 4. So, so these are labeled by the three Cartans H1, H2, H3 of SO6, and the conformal dimension delta, which classifies representation under O2. Um, and um, sorry of and yeah, sorry, and the R symmetry representations D1 and D2 are classified representations under SO5. So these are the Cartan um, 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 sorry um, yeah, so these are the weights of the representation basically. Yeah, and the super um, the unitary representations of OSP 8 star slash 4 has been studied in the literature, and they have been classified into the following 5 types. So we have the long representation for generic delta 1 delta 2, and their dimensions are given in terms of the corresponding um, SO6 weights and the SO5 weights in this particular manner. So in particular, delta has to be greater than 6. This is the important thing to keep in mind. So delta begins from 8 basically, or from yeah, okay. Like in large N theories, it will begin from 8. This is the important thing to keep in mind as it will appear later. Next, we have like these A theories, which are the the A type supermultiplets, which appears when L hits the unitarity bound. And then there are a bunch of there are a bunch of representations which are not continuously connected to 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 the to the long representations. Um, the half BPS representations are of the D type, okay, and these are and these are and on top of that they are the symmetric traceless representations of SO5. So the D1 component is non-vanishing, whereas the D2 component is 0. Moreover, delta is given by twice. So I mean, so if, for an operator OP which lies in this particular representation dp comma 0, the conformal dimension is twice the value of p. So this is all just representation theory so far. In AN theories, um, all integer values of p which is greater than 2 appears. And in DN theory, the Z2 orbifold basically projects out all p, those which are odd, and only the even p survives. So this is the spectrum of half BPS operators in AN and DN theories. Now for p equals to 2, there is a unique operator O2, which is the bottom component of the stress tensor multiplet. And what we are interested in is the 4-point function of this operator O2. Now, since we saw that it is a symmetric representation of SO5, which is labeled by 2 indices, since it's a rank 2 tensor of SO5, so there are two indices here, I1 and I2. What we do is that we contract this with a null vector of SO5 in the following way and obtain this particular representation, which we will eventually work with. So what we are interested in are 4-point functions of this operator, which on account of R symmetry and conformal symmetry um, can be written in this particular way. So we can pull out this prefactor and call everything else as this curly G function. Now, one important thing that I should mention here, that this curly G function is a degree 2 polynomial in sigma and tau, which are the cross ratios of SO5 that are constructed from these null vectors Y.
Then what are U and V?
U and V are the cross ratios in that are constructed using x1 and x2, x3, and x4. So there are
Right.
two kind of so since this operator lives in um, both space time and some R symmetry, and like in some global symmetry group, we have to account for the global symmetry factors as well, right? So it will generically be a function of not just the SO6 comma 2 part, but it also be a function of the SO5 part.
Right. Okay.
Okay.
Mhm.
So this is the important function that we will be studying. Now, so this is up to now, everything is just bosonic part of the superconformal algebra. But then we also have the fermionic part, and the and those form the so-called superconformal word identities, which was computed by Gallo, Dolan, Gallo, and Sukachev. Um, and it just takes the following form. I mean, there's no better way to present it. I mean, this is just this particular representation where Z and Z bar are related to U and V in the standard way. I mean, we have U equals ZZ bar and V equals 1 minus Z, 1 minus Z bar. And similarly, sigma, tau, and alpha alpha bar are related to each other, like sigma equals alpha alpha bar and tau equals 1 minus alpha and 1 minus alpha bar. So that's the relation. Um, so this is how the word identity constrains this function curly G. And this is for, I should have mentioned that this identity is for a generic 4-point correlator of half BPS operators. Okay, for generic meaning, like for not just O2, 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 but for like okay, 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 okay. So this is the superconformal word identity which constrains this function curly G. And as a consequence, and one of the consequences of the superconformal word identity is that this function G can be expanded into superconformal blocks. So what we see here is the decomposition of curly G into the super blocks corresponding to the super multiplets which appear in the OPE decomposition of O2 with O2. So we need to know what are the OPEs, like which operators appear in the OPE of O2 with O2. Okay, which super representations. So let me comment on that. Um, so we saw all these representations earlier, right? So what appears here are the identity operator, the operator O2 itself, and then a bunch of double trace operators. So there are 4 kind of operators which are protected, and then there is a series of operators which is unprotected, the L00. The D's are all scalars, and the B's have spin. Okay. Um, the B20 has even spin, and the B02 has odd spin. Um, so um, and the D40 and the D04 are obtained by taking basically the projection of O2 and O2. Uh, and, uh, I mean the respective like projections of O2 with O2 on the specific 4,0 and 0,4 of SO5. However, the single trace, but there's also like another operator, which is a single trace operator, D40. Now this is the D40 that appears here is the double trace guy of these 2 operators. There is another single trace operator D04, which is also in D40, but this particular operator does not appear in O2 with O2. So this is like a important thing to keep in mind. So the only single trace operator is this one, and the rest are double trace operators. B's the form of the operator B20 and B02 are presented here. So I mean, it's basically insertion of derivatives in this manner, and then taking the respective projections under SO5, which is 2,0 and 0,2. The D and the B operators are sorry, the D 2 n comma 0 and the B 2 comma 0 are what are known as chiral algebra operators, and the OP and their OPE are 1 over C exact. So this was a result which was derived by Rastelli and collaborators, where they identified a particular uh, um, subsector of the 62,0 theory, which enjoys an enhanced symmetry, which is the WN algebra. And from the OPE coefficients, basically from the structure constants of the WN algebra, one is able to compute the OPEs of this guys exactly. And for 2222, for like O2 with O2, these are known to be 1 over C exact. So this is like some known result in 62,0.
Excuse
Okay.
me, I don't know exactly what it means to be 1 over C exact. Can you please explain what that means?
Okay, I just mean that they terminate at order 1 over C.
Okay, fine. Hmm.
Yeah, so like for 2, 2, 2, 2, the OPE coefficient of like lambda 2, so lambda 2 comma 2 comma um, like D20 is some function, like is some function of 1 over C, which is like just 1 over C. I mean, there's is not like a series expansion 1 over C.
Okay,
And
okay,
similarly for B20.
okay,
But for like 3, I mean, if you were to consider like O3, then this is like a non-trivial 1 over C expansion.
right.
So this is like known from some protected subsector of 6D2, 0, like these two OP coefficients. Um, what Okay, so this is that, and then we have the long operators, this L00, which has unprotected dimension delta and the spin L, and these are and their dimensions are given by so it's 8. So 8 comes basically from the fact that there were like two operators O2, right, and each of them has dimension 4, so 4 plus 4, 8, and then there's the insertion of a bunch of boxes, so that gives like a 2n, and single derivative, so that's an L, and plus some anomalous dimension. This is the standard unprotected double trace operator um, conformal dimension. Now for a fixed delta naught, where delta naught is this object here without the anomalous dimension, there are a multiple number of double trace operators in this particular representation. Okay, and just to tell you what these representations, like what these multiple operators are, I show you here that so for example, if we fix L and N, then we have sorry, if we fix and delta naught, then we have this particular operator O2 with O2. Then we have this operator O3, O3, but then on the power of the box reduces by 2, right? And so on. So it goes up to all the way up till OP, OP, and then the power of box is this particular exponent. All these operators, as you can see, lies in this particular representation. They're conformal, their conformal dimension without the leading order conformal dimension is the same, and they are all singlets under SO5, and they all have the spin L. How many such operators are there? Well, I mean, we can just demand that the power of the exponent is positive, right? Because we want to construct some local operators. And then that basically constrains us that P should be in the range 2 and the integer value of tau over 4. So there are these many words of these many numbers of operator for a given value of the twist. Now, um, so if the twist is greater than 12, right, then there are more than one operators, and this gives rise to the problem of mixing. There is a degeneracy among the unprotected operators, and then which leads to a mixing problem. So this will be important later on, and I will come back to it at some point. Um, okay, so one of the things that I mentioned previously was the super block decomposition of the 4-point function. The super blocks themselves are like finite linear combinations of ordinary conformal blocks, and the finite number comes from the fact that in a given irreducible representation of OSP 8 star slash 4, there are finite number of operators. However, it is very difficult to work with these super blocks because they are a bunch of there are several operators which contribute to a given super to a given irreducible representation. So what one does is to work with so-called reduced correlator formalism. So let me explain what this formalism is. So as a consequence of the superconformal word identity, this this equation here, one finds that the solution, like a solution to this identity, is to write down G in the following way. So we have so we write G as some function f plus a differential operator gamma that acts on H, which we call the reduced correlator. This function f is 1 over C exact, and all the non-trivial information in the theory is given by the function h. So f we know exactly because of the chiral algebra, but h is something that we have to compute. So we basically decomposed this problem, which was of bootstrapping this function g, which was a function of sigma and tau, to ultimately bootstrapping a function h, which is no longer a function of sigma and tau. The operator y here is quadratic in sigma and tau, and basically contains all the sigma tau dependence. So all that we have to work with is this particular reduced correlator h. And more important, so this was for the correlator itself, but more importantly, the super blocks themselves admit a decomposition of this kind. Okay.
So,
uh,
excuse me, this y or epsilon that you have,
yeah.
that its structure is fixed by specifying what are the operators that we are studying.
No,
I
no, no.
mean,
It's not an operator dependent. Like, well, it's not like operator dependent operator. I mean, it's an op. So y is a differential operator,
yeah, sure,
which which
but
which is a
you
consequence of the superconformal word identity.
right.
So the form is fixed,
Okay,
irrespective of which 4-point function you're looking at.
I see. I see. Okay.
So this is like a universal decomposition. What changes according to different correlators are these functions f and h. So for example, for the O2, 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 O2 4-point function, f is 1 over c exact, and we know it from the chiral algebra. H we do not know. So h is something that we have to bootstrap.
Okay.
But why is and these two then are connected to like related to this full 4-point function in the following manner. Now,
Okay.
this is for the correlator. The important thing that I was telling before was that such a decomposition also works for the super blocks themselves. And the very nice thing is that for the 2 to 2 to 4-point function, this h is just a one single block, one single 6D block, which is very nice. So instead of working with finite linear combinations of several conformal blocks, which constitute a super block, we now have to work with just one with just one 6D block. So, for example, if you were to give me h somehow, let's say that you somehow computed h, then I can compute the CFT data by expanding h in the following way, where I'm basically presenting to you what what the reduced blocks are. So the reduced blocks in this case are basically shifted. So first of all, these are no longer conformal blocks for identical operators for identical for external operators. I mean, like delta 1 2 is 0, but delta 2 3 4 is -2. So this is like a shift. And then moreover, we also have a shift in the dimension of the exchange. So like if we had a dimension delta operator exchange, then in the reduced representation, what we have is delta prime plus 4. So this is some detail. I mean, all I'm telling you here is that this function h admits a nice conformal block decomposition, a nice 60 conformal block decomposition. The existence of this kind of a block expansion is actually highly non-trivial as a consequence of a supersymmetry word, superconformal word identity, as I was mentioning earlier. And until recently, it was only known for correlators of the form 2 to pp. However, we also now know how to compute these for the generic, for correlators which are in the generic representations of SO5. But the form is not very nice. I mean, the form here was that of a single 6D block. But if, for example, if we were to study 3 3 3 3 4-point function, then this is like a horrible expression. I mean, here it was just like a block over U, but in for example, in the case of 6 6 3 3 3 3, this is like a sum over several blocks and multiplied with functions of U and V. But for some, but it's still important, like convenient to have those representations, because reduced correlators are generally more convenient since they are down by a power of 2 in the R symmetry polynomials. Anyway, so that was the block expansion. Uh, so now the comes the main point. So we want to study correlation functions in a 1 over C expansion, and I was saying before f is 1 over C exact. So this is the form. So here I present what that function is. So first of all we have the disconnected piece, which is 1 plus the standard form 1 plus sigma u square plus tau square u to the 4 v to the 4, and then we have the 1 over C piece, and that's it, and there's no further 1 over C square term here. On the other hand, the reduced correlator edge has a non-trivial 1 over C expansion. So it starts at 1 over C, then there is a 1 over C to the 5 thirds, then we have 1 over C square, and so on. So, and the reason that we are seeing this funny powers of 1/3 in 1 over C expansion is because we chose to write this in a central charge expansion. If we were to write this in a 1 over N expansion, I mean, if you remember from here, that the central charge scales like N cube. So if you were to trade this C for N, then this will all be integer powers of N. Okay, so this is the expansion that the reduced correlator exhibits. Correspondingly, we should also expand the conformal dimensions and the OPE coefficients of the operators which appear in this particular 4-point function. And what happens?
What do the R and R to the 4 and R bar R stand for?
Yeah, so this is something which I will explain. So I'm just telling here that, so I mean in hindsight, just recall that we are going to ultimately map this object H to some scattering amplitude in M theory, right?
Right.
Um, so if you just keep that in mind, then as we saw in the introduction, um, uh, I mean, there were these contributions that goes like the supergravity term, then R to the 4 term, then the D to 6 out of the 4 term, and so on, plus loops. And loops can come from various vertices. For example, loops can come from R and R. It can come from R and R4. It can come from R4 and R4, and so on. So
Hmm.
what I have shown here is basically the contribution of those vertices. So this would be a contribution from the R to the 4 term in the. So if, for example, if one were to holographically compute this 4-point function and look at the contribution from the R to the 4 term, then this is what I would label that term as.
I see.
This will be the supergravity term, this will be the R to the 4 term, this will be the one loop term that comes from combining two supergravity vertices. So this is like a systematic expansion that we would, so this is like some expansion that we expect based on what we know in about scattering amplitudes in M theory. Yeah, so that's that, yeah, okay, so this is like the expansion that we expect for the correlator, and correspondingly we also expect an expansion for the operator dimension and the OP coefficients. Now at tree level, the expansion for takes the following form. Okay, so this was for the correlator, but then we also can expand the right hand. So this thing compares to can be expanded in conformal blocks, as we mentioned in the previous slide. So we were expanding this, but now let's say that we want to expand this object. So how does that expand? So that expands like follows. So for all those operators which are not which are protected, right, which are not in the representation L, for them the expansion is only for the OP coefficient, right, because they don't get any anomalous dimension. For the operators which are not protected, they also get a contribution from the anomalous dimension. And the important thing to keep in mind is that the anomalous dimension always comes with a log u, right? Because the conformal blocks themselves goes like u to the power the anomalous, the dimension of the operator. Sorry, the dimension of the operator. So when we take the derivative, we with respect to the dimension, we get a log u. So this is the structure that we have at tree level. I mean, like at the first non-trivial order. At one loop level, we have a similar structure. I mean, so this would be the the contribution from the protected operator. Okay, so one of the things that I should maybe go back and recall is that this was the spectrum, right? So we had the spectrum D20, D40, D04, B20, and B02. So among in this spectrum, this guy D20, D40, and B20, these are 1 over C exact. Okay. And they terminate at order 1 over C. That means they don't get a contribution at higher order in C. So all that appears at one loop level here are the D04 and the B02. These operators D04 and B02. Um, right, so these are so these would be the protected operators which appear here, but their OP coefficients are not protected. I mean, they get like a non-trivial 1 over C corrections. But then for the unprotected operators, we have the following structure where we have organized the contributions as powers of log u. So we have a specific log, we have a log u square, we have a log u, and we have a 1 here, which is the so yeah okay let me explain briefly what these terms are. The log square u, the coefficient of log square u is completely depends upon the tree level and the zeroth order quantities. So gamma r is the contribution that one would have gotten from the tree level um, correlator. Okay, so this comes from here, and lambda 0 analogously like one gets from the zeroth order, basically from this piece here, from this piece, so one C to the 0 piece. So the important thing is that this particular piece can be completely bootstrapped by knowing the previous order term in the 1 over C expansion. So okay, so that's for the log u piece, there is the new quantity gamma rr, which is the 1 over C square correction, or the next higher order correction to the anomalous dimension. And the piece which is independent of log u contains the one loop correction to the to the OP coefficient of the unprotected operator. So the unprotected operator gets corrections both to dimension and the OP coefficients, and it's contained in this line. So this is the structure of conformal block decomposition in a 1 over C expansion. Okay, so now we are in a position to so we have reviewed both the left hand side and the right hand side of this equation in 1 over C expansion. Um, um, so basically we want to compute HRR, and the question is, how do we do that? So we start from this term, the log u square term, because we know this the coefficient from the previous order result, the tree level result and the zeroth order result. So this is the thing that we have to compute. This is the sum that we have to do. And to do this sum, we basically, first of all, we need these coefficient, this particular coefficient here. So what is this coefficient? So this coefficient depends upon um, the kind of unprotected operator which appears. And what are these protected operators? We already saw them. These are of this particular form, OP with a bunch of OP with a bunch of derivative insertions. And the key thing to note here is that this particular operator I appears in the OPE of both O2 and O2 and with OP and OP. Okay, so if somebody gives me the 2,2 pp tree level correlator, so this okay, so this is something that people have already known. I mean, there was a paper by uh, Shinan and some I think there was a paper just by Shinan where he computed this particular tree level correlator just by using superconformal bootstrap, which was developed earlier with Rastelli and others for the case of n equals to 4 superangles. So this object is known. Okay, this 2,2 pp correlator at tree level is known. So the key point here is that if we know the log u piece of the 2,2 pp correlator, which we know, then we can extract this quantity. right? We can extract the so what appears here are the so log u piece. The coefficient of the log u piece is the following. So it is the OP coefficient of O2 with I and OP with I times the anomalous dimension of the operator I. And what we extract here is the sum. So sum over I. Okay, so this is something that we can compute because we know the tree level correlator. So from the correlator we can expand in blocks, and from the blocks we can read off this term. So once we know this object, we can then square it and divide it by the pp by the square of this object, which is the zeroth order OP coefficient involving p with p. So the problem now boils down to computing this, which we have computed, which I've told you that we have computed, but then we also need to compute this. So the sum that we are seeing here, the sum over zeroth order OP coefficient times the anomalous dimension whole squared, takes the form of a sum over P of this complicated object. Now, okay, so this was a bunch of detail, but the important thing is that what is what I'm doing here is I'm solving this mixing problem, which I was telling like a few minutes ago. Since there are these bunch of operators which are degenerate at leading order in 1 over C expansion, we need to somehow unmix them, and this is the procedure of doing that. Um, so this was for the AN theory. If you want to do it for the DN theory, then in this sum, you just take P to be even. You just project out all odd P's. So this is basically the only, at the technical level, this is the only difference between the AN and the DN theories. So just to put like whatever technical details I said here in pictures, what we are doing is that so we have like external graviton states, external states, right, which are O2, 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 and O2. And what happens is that in the bulk, there's an exchange of Kaluza-Klein modes, and these run in the loop. If we were to like cut this diagram and some kind of if we can develop some kind of an ADS unitarity method, then this can be written as a sum over products of written diagrams of this kind. So we have like 2 to pp, 2 to pp, which is what we are computing here. So this is so we know the numerator, and then we also know the denominator, which was a very hard calculation. But anyways, I mean, I will not go into the detail. But we have computed the OP coefficients, the generalized free field OP coefficients that appear in PPPP, and we have also computed the anomalous dimensions regarding 2 to PP. By the way, this was the reduced correlator which in 2 to pp, which I was talking about earlier. So it is given in terms of some d bar function with labels 2p plus 3, 2p minus 1, 3, 3, whatever. Yeah. So putting these two results together, we can in this formula we can then try to do this sum over conformal blocks, which takes the following very nice form. I mean, so we can organize this sum as a power series expansion in Z with coefficient function in Z bar, and these coefficient functions take the following very nice form. So it's a coefficient. So it's a function in Z bar, and of weight of transcendentality 2. So it has a log square piece. It has a dilog piece, it has a log 1 minus z bar piece, and it has a 1. So this is so these are the four, if you want, like the basis functions in which we can write down these coefficient function h in here. Ideally, what we would like to do is to also do this sum over n, and this was done for the case of n equals to 4 super Yang-Mills. But for the 6D case, we were not able to do this sum. I mean, we tried, it basically it requires some kind of an answers, but to do this kind of sums, but all the answers that we knew we are aware of do not work here. Some new structure appears. So this is like an unsolved problem at the moment, but it
And
never,
this
never.
P, excuse me, the P1s and the P4, I mean the P1 to P4, what are
Yes,
they?
yes. So these are just the polynomials in Z bar of degree, which is given in the curly brackets.
Okay. Okay.
the
Mhm.
curved bracket. So this,
Yeah, yeah.
yeah, so these are just some polynomials.
Mhm.
So this is a very nice form. I mean, and this was all sensitive to this particular coefficient here. I mean, if this coefficient was even a little bit wrong, we would not be able to guess this nice form. And the appearance of functions which are of transcendentality 2 is basically a signal that we are like in the right direction, because these kind of functions appear in one loop correlators. Okay, so that's so this was the like the result in position space, but and the result only for the log u square piece. Remember that the full correlator has all these like, I mean, it will not just have log u square piece, it will also have a log u piece, and then a one here, and then the contribution from the protected operator. So all that we have here so far is this guy here. Okay, so we now have to also find out what the other remaining pieces are. And to do that, what we will do is to basically go to Mellin space now. So let me first briefly mention how the Mellin transform works here. So the reduced amplitude H is related to the Mellin amplitude, the reduced Mellin amplitude M, in the following way, which is a standard way, but this is like the standard relation, but then the powers are slightly different for the reduced amplitude. Anyway, so and also this relation S plus T plus U is also different. But but okay, but like this is some formula that one can derive um, using using the superconformal Ward identity. Um, um, and furthermore, this amplitude MST. So this is the amplitude that we are interested in, MST. And the important thing is that this amplitude satisfies crossing symmetry. So MST should be equals to MSQ should be equals to MTS. Now, just like H, the reduced correlator H, M also has a non-trivial 1 over C expansion, and it follows the same pattern. So we have the contribution from the supergravity term, we have the contribution from the R to the 4 term, and then we have the contribution from the loops. Um, I will maybe I should skip this detail, but okay, I think it's relevant. Yeah. So so this was the reduced amplitude M. We also have a formula for the full amplitude. So remember, there was the reduced correlator and there was a full correlator, right? So similarly, we have a reduced Mellin amplitude and a full Mellin amplitude. So for the full Mellin amplitude, the structure is of the following form. So we have some exchange terms, exchange contributions, and we have some contact contributions. Um, and in the exchange contributions, we also have some contact terms, but then the coefficient here and the coefficient here are unrelated. So the coefficient here is fixed by the Ward identity. So this is like the generic structure of the exchange Mellin amplitude. Up to an overall coefficient, this structure this is the structure at tree level. Okay, this is all at tree level. So this up to an overall coefficient, the structure at tree level is fully determined by the following four quantities. So the poles of the single trace exchange. So these are operators whose twist is less than 8, because all the protected operators were of twist less than 8. Two, the asymptotic behavior at infinity. I mean, how these functions grow as a function of the Mandelstam variable S and T. Three, which is the superconformal Ward identity, and four, which is the crossing symmetry. So these four bootstrap conditions, if you will, if you want, completely constrain the tree level Mellin amplitude up to an overall coefficient. The form is completely fixed. Um, so so um, so this is how actually people have computed tree level ADS correlators until recently. So for example, this particular function here that we solved for 2 to pp was actually obtained in that way, in that particular manner, where we were where what people did was to bootstrap the Mellin amplitude and then convert it back to position space. So that's the practical route. Um, Okay, so that's given. Yeah, and then another important thing is that the full Mellin amplitude is related to the reduced Mellin amplitude by now a difference operator theta, so which is a consequence of the superconformal word identity. And just to give some examples, that for the tree level term, the Mellin amplitude takes the following simple form. So it has like 1 over s minus 6, s minus 4, t minus 6, t minus 4, u minus 6, u minus 4. So this is like the reduced amplitude for m for the supergravity term, and then this is the reduced amplitude for r to the 4 term. The overall coefficient hash here can be fixed by taking the flat space limit and certain protected quantities. So these two are exactly known. Now, now here is the main result of our computation. So we know that. Just recall here that there is this particular log square 1 minus z bar piece, which is nothing but log v if we convert this to uv variables. So and this was multiplying log u square. So like um, what I'm stressing here is that there's a log square u log square v piece in the in the one loop correlator. Now, how like to what kind of quantity does log square u log square v piece match? This matches to simultaneous poles in S and T, which you will appreciate when you look at the form of the Mellin transform. So if you have a simultaneous pole in S and T, then you will pick up log U and log V at the same time. Okay. Um, um, so this is so that's the form. From the appearance of this kind of term, we know what is the form of the Mellin amplitude, and just plug in just using that form as an answers, we are able to reproduce basically MST, which we are able to calculate MST and the Mellin amplitude, which reproduces the entire log U slice. So it not just reproduces the log V term over here, but it also reproduces the dialog, the log 1 minus z bar, and the 1. So, so okay, so just by focusing on this term here, one is able to basically, if you want, like guess the full Mellin amplitude, which we also then crossing like crossing complete, and because we know that they satisfy this kind of crossing symmetry relations, and then we are able to like guess the full Mellin amplitude. So, for example, for the the contribution from the supergravity takes the following form. So it takes the form of an infinite sum over double poles, and a single infinite sum over single poles. So and the non-trivial quantities here are these residues Cm and Cmn. For example, the Cmn, I am not presenting the full the residues here, but they take this following complicated form. So it's like a complicated ratio of gamma functions times a polynomial of degree 7 in m and n plus another ratio of gamma functions times a polynomial of degree 9 in m and so on. Yeah, so it's a complicated beast. Yeah, and so on. So this is the term, and then we also add the crossed pieces. So this is basically the end result. So this is the one loop supergravity correction to the 4-point function of the stress tensor multiplet in 6D2,0 theory. Now, a few comments. The singularities of this one loop term are an infinite set of simple poles, and there are no branch cuts in. Okay, so this is an ADS. Now, if one were to take the flat space limit, this sum would turn into an integral, and in that case, all the simple poles would then like coalesce to form a branch cut. So that's and so that's how the flat space limit counter of the statement that simple poles turn into branch cuts apply. Um, Now, okay, but I should have mentioned that this is not the end of story. There could also be, in principle, contact terms which are undetermined with an overall undetermined coefficient, and this is something that cannot be fixed by the computation that we have done so far. In principle, this is allowed. I mean, and they are perfectly fine. I mean, these are completely consistent with the log U term that we had, and also consistent with the superconformal water identity. But the coefficient here is something that we cannot determine through this approach that we have been discussing so far. So that was the contribution from supergravity. But we also have computed the contribution from supergravity r to the 4 and r to the 4 r to the 4, and the structure takes the form of a single sum. In this case, there is no double sum; it's just a single sum. Um, um, okay, let me check
I
how much
think
time.
if we could summarize now, it would be
Yeah,
good.
yeah, I think I was actually about to summarize that in the next slide, but just let me like briefly tell what the flat space limit is.
Sure.
So this was the amplitude in ADS space, right? In ADS 7. Now, now in a paper by Penedones, where he conjectured the flat space limit formula, that relates the Mellin amplitude in ADS to the flat space scattering amplitude by this particular relation, where there's some kind of an integral involved. And if we apply this formula here, we find actually a precise match. I'm not presenting the details here, but all that I want to say here is that like what happens is that when we convert this sum to so okay, I mean, I should have mentioned that we know how the element the amplitude as a function of beta s times beta t. If we take beta to be large, we know that it scales like beta to the 3 half. This is something that is a given which we know. Now, this behavior, I mean, if you look at the amplitude itself, I mean, if you multiply S with beta and T with beta and take beta to be large, you get 1 over beta squared, right? You don't see beta to the 3 half. So this basically means that this kind of behavior is reproduced by an infinite number of terms where the in the sum like from the tail of the sum, from where we see that from where we will actually capture this beta to the 3 half behavior. So we also take m and n to be large in this sums to see the flat space limit. Okay, so what we basically do is to take m, n, s, t, all of the same order and convert the sum to an integral. And then we then put it in the Pendonis formula and we find a precise match. So, okay, this is some detail, but I'm just take my word for it that like we have like done this carefully for both the single sum and the double sum. And when we add the two, we exactly match. So this is the known result. And this is like a non-analytic function, as you can see the square roots and 3 halves and so on appearing, which we were expecting. And we can repeat this also for R4, and for R supergravity R to the 4 and R to the 4, R to the 4 vertices.
So you're saying that the right-hand side of that equation that you just showed is something that matches the work of someone else.
Yeah,
So
so yeah,
yeah,
so the sum of the the right hand side of the first equation and the right hand side of the second equation is known. So people know this. And
right,
I am saying that we have reproduced this right hand side by purely CFT computations.
right. By that scaling that you just said.
Yes, so we know the Mellin amplitude in ADS, and that is a sum, that is a discrete sum. There's sum over numbers, right? So there's a double
Right,
sum involved, and I'm telling you how to reproduce it, like
right.
how to. So in the previous part of the talk, I was telling how to compute this. Once we
Hmm.
have this result, we then have a procedure to check how to reproduce the 11D scattering amplitude, which is what I was explaining here.
Yeah.
So what we do is to take the like look at the tail of the sum, take m, n, s, and t to be very large or not the same order, and then convert the sum to an integral, do the integrals, and and just read those like the answer. I mean, that's the answer basically. And you
Mhm.
can do the same thing for like r to the 4, r to the 4, and supergravity r to the 4. So what we have
Okay.
computed are basically these three diagrams. So this is like the summary that these this is like the R to, so R supergravity vertex is basically a box diagram, which because of the exchange term, the R to the 4 supergravity term is composed of a contact diagram and two exchange vertices, and the exchange vertex, which is a triangle diagram, and then R to the 4 is a bubble diagram. So we have computed these three Witten diagrams on ADS 7 times S4, and then we have also checked the flat space limit. So,
Right.
so this was some. Yeah, here I was. I wanted to explain how people have computed the 11D one loop amplitude, and this is like a well-known paper from by Michael Green and collaborators, where they look at like the two part. So like they look at the discontinuity of the amplitude, which they know how to compute because of maximal supersymmetry. Things simplify, and people know the the discontinuity in the S channel, and from the discontinuity you can reconstruct the full amplitude. So okay, so let me end there. Okay, I just wanted to mention that so now that we have like the full one loop correlator, from the one loop correlator we can now compute the one loop corrections to the CFT data, and this is also something that we did in the paper. And yeah, so and yeah, so yeah, so we, okay, just to show that we had some actual results. I mean, like, so the spinning operators b 02 of these spins take the following form. So interestingly, they take the form of a rational number plus another rational number times pi square. So this is the kind of this is the kind of corrections to the CFT data that we have.
Hmm.
um, yeah, so this is like this is like the exact form. There's no numerical thing here.
Is there
uh,
some structure to them?
like a general formula as a function of spin.
Mm-hmm.
Well, we didn't compute enough spins to. This would be very hard actually, because for sure there is something hidden there, because these are like um, I mean uh, I mean, it's like in string theory, people have been, sorry, in the case of n equals to 4 super Yang-Mills, people have been able to compute like the closed form function. And there are specific kind of functions which appear for the OP coefficients. Presumably something similar will also happen here. But as you can see, these are so complicated numbers, and they grow very like in a crazy manner as you increase the spin. So yeah, I mean, I mean, if you know like sufficient number of them, like try to put them in Mathematica, do a fine sequence. I don't know, maybe it gives something,
Right.
but yeah, I mean, in this project we were not able to. I mean, we actually bother to compute so many spins and actually computing these numbers is quite hard. I mean, it's not straightforward.
Okay.
There are several ways to do it. I mean, one is the inversion formula, which we do in the paper, and one is also from the Mellin amplitude. So we did the computation through both the methods, and we found the same result. So that was like a consistency check of doing in two ways. But then computing many of them actually is a bit complicated. But it could be done. I mean, we just didn't bother to do it.
Okay.
Yeah, so that was for the maybe I'll skip 3D and equals to. This is like a work under progress, and there are some new developments here. But let me just mention that the form of the amplitudes here are also of the similar kind. For example, for R4 is exactly the same form that we found in the 6D case. But there's some, okay. I mean, I'm actually way over time, so I think I should just stop. So maybe I'll just conclude. So
Yeah.
what we did, so what we calculated in this project was the one loop correction to the stress tensor 4-point functions in 6D2, AN and DN theories at order R supergravity R to the 4 and R to the 4 R to the 4, which corresponds to 1 over C square and 1 over C to the 8 thirds and higher power of 1 over C. We have also computed the above quantities for the case of 3D n equals to 8 ABJM theory for rank 2, and found similar structures. The details are different, but the structurally the results are quite similar. And the flat space and the corresponding flat space limit of the amplitude in ADS 7 and in ADS 4, both of them we should expect to match to the same object in 11D, and we find that that happens. So this is another nice thing that we found in 3D. Um, um, and in 6D, we also computed the CFT data, which from the one loop created 4-point functions. And okay, just ignore this comment here because I didn't present details of the CFT data. But yeah, okay. And some future directions maybe I should mention is that the 4-point function of higher Kaluza-Klein modes, like not just 2 to 2 2, like what generic PQRS are like obvious targets. However, there is like technical difficulty due to so this was done, so this can be this was attacked. So this actually 4-point function was dealt with in the case of n equals to 4 super Yang mills, because there the reduced correlator technology is known and it's convenient to use it. But for the case of 6D, there is no convenient reduced correlator technology, and also there is no 11D conformal symmetry. So here the 10D conformal symmetry was important to write down. The hidden 10D conformal symmetry was important to write down the PQR as 4-point function at one loop. But in 11D this is a bit difficult. But at the moment we are currently looking at 2233 and 3333 4-point functions. And one of the question is there is a systematic way to compute 22pp. Another set of theories that one can look at in this program are theories with reduced supersymmetry. So examples are like D1, D5 CFT in 2D, the n equals to 6 ABJM theories in 3D. And these are like dual to product spaces of the times of the type ADS times some compact space M. Other examples of half maximal supersymmetry include warped ADS spaces like holographic duals of 5D n equals to 1 theories, or the 6D 1,0 theories. And then like, what about non-conformal field theories? What can we say about those? Even at tree level, yeah. So yeah, so that's all I wanted to say, and thank you for listening.
Thank you so much. Well, I have asked all that I wanted to ask, actually. I mean, I stopped you a lot.
Yeah.
If someone else has something else to ask, we had more who were part of the seminar, but they have left by now. So I guess don't
Yeah, I
have
guess it's
anything more to ask right now. But I'm sure they will write to you. And if I could have your slides, I can also share that with everyone else.
okay. I'll
And
send you the slides. Yeah.
yeah,
Yeah.
thanks. Oh, okay, I will stop the recording now.
Okay. Thank you.
Thank you. Thank you.